The next thing I want to look at is a pendulum. We usually think of a pendulum as a mass at the end of a string, and we can displace this and it oscillates back and forth. In order to be a little bit more complete, we sometimes call this, rather than a string, a massless rigid rod. Now, why is that important? Well, if this were actually a rigid object, then we could actually bring the pendulum all the way up here and have swings which actually go past the horizontal. With a string, obviously, if I bring this up here and I let go, it doesn't swing around this way, it just drops straight down. But if we had a rigid rod, we'd be able to have oscillations go all the way up even past horizontal. Massless, because we don't want the string to have any mass, we just want to imagine a point mass at some constant distance, we'll say L, from the point of support. We'll stick our origin up here, so we want this to be some constant value L. If we had something that did have mass, maybe a more complicated object, we'd have what's called a physical pendulum, which is a bit more complicated. We'll take a look at that later. But for now, let's imagine we've just got point mass, the end of a rigid rod, and we displace it. Let's imagine we displace it at some angle theta from the vertical. So here's our equilibrium. We're going to displace at some angle theta. Sometimes this can be treated, or this is treated, using forces F and M, F equals ma. What I'd like to do is do this a little bit differently, because we basically have something that's going to move around on the arc of a circle. I'm going to use torques to take a look at this and see what the behavior is going to be. So here's our point mass. What forces are acting on it? Well, we know we're going to have a force of the weight straight down. So we've got weight, which will be mg. We also know, because it's tied onto the string or the massless rod, whatever, we're going to have a tension in this direction. Okay? Rather than looking at the forces now, I want to convert all of these to torques. Let's calculate what the torque is. Where should we put the origin? Well, let's put the origin up here at the point of support. Okay, so there's our origin. So what is our net torque? Well, we've got two forces, so we have to consider two torques. Let's imagine that the length of our pendulum is some length L. What does the torque do to the tension in the string or the rod? What's the torque due to the tension? I want you to think about that for a second. See if you can figure out what the value is. Well, remember, torque, so I'm going to put the totals over there, but let's remember torque, by our definition, is RF sine theta. Remember, R, what's R? R is the distance from the origin to the point where the force is applied. F is the force. Sine of theta is the angle between the vectors R and F. So over here, R for the tension will be the length L. F is the tension. But what is this is a little confusing here. Maybe let's, rather than this theta, maybe we'll call this some angle phi for the moment, so as not to confuse theta necessarily with the angle phi. What is theta for this equation from this diagram? What's the value of theta? Remember, it's the angle between R and F. Well, what's R? R is the vector that goes from the origin to the point where the force is applied. The force is being applied down here on the mass. So here's R. What's F? F is the tension, which is going back up this way. So what is theta? Theta is the angle between R and F. R, F, what's the angle between them? It is 180 degrees. So for the tension, the angle between R and F is 180 degrees. What's sine of 180? It is 0. So in other words, the tension is not exerting any torque on the mass. In other words, the tension does not tend to make the mass rotate around the origin. Okay, very interesting. That contributes no torque. What about the torque for the weight? Well, what is R for the weight? Again, R is the distance from the origin to the point where the force is applied. It's the length L. What is F? Well, it's just the force, mg. And then sine. What is theta from this equation. In other words, what's the angle between R and F? Well, let me make my R here again. So here's R, here is F, straight down. What's the angle between them? Well, we'll put them tail to tail, straight down. What's the angle between R and F? Well, it's exactly how we defined phi. So theta now for the weight is our angle phi. So in this case, sine phi. Okay, now that we've gotten that confusion between the angles, I really would like to go back to calling this theta because it is our angular position quantity. So let me just come back and call this theta. There we go. Now, what is tau, the torque? Well, that's the value of the torque. Sorry, that's one more thing I forgot. Is this going to be a positive or negative torque? Well, the weight is tending to move the mass back in this direction, in other words, in a clockwise direction, which is a negative torque. So we have to put in a negative sign. There we go. That's the torque. What is Newton's second law in terms of the angular quantities? It is tau equals I alpha. So this must be equal to I alpha. And what is I? Well, for a point mass, a mass m at a distance L from the origin, the angular moment, moment of inertia is ml squared. So this is going to be ml squared times alpha. Now what is alpha? Well, in terms of the angular quantities, alpha is the derivative of omega. Omega is the derivative of theta. So alpha is d squared theta dt squared. What do we have? Let's bring this to the other. We can leave this any way we want. Let's maybe bring this to the other side. We have d squared theta dt squared plus lmg sine theta divided by ml squared equals 0. One of the l's cancels, the m cancels, and we end up with d squared theta dt squared plus g over L sine theta equals 0. There we go. Is this simple harmonic motion? From our, when we looked at the mass on a spring, we found that d squared x dt squared plus k over m x was equal to 0. And we said when the acceleration was proportional to the negative of x, so put this over here, we have negative x, negative k over mx, or in this form where this is omega squared, we got simple harmonic motion. Is that what we have here in terms of theta? We do not. We do not have theta here, we have sine theta. Because this is not proportional to the angle itself, it's proportional to the sine of the angle. The motion of the pendulum is not simple harmonic. So even though when we look at this, it looks very similar to harmonic motion as it's going back and forth and back and forth. It looks like we could describe it with a cosine or something like that. It's not exactly a cosine. Now, how can we be sure about this? Well, what's the difference between whether this were sine theta or whether this were just theta? What's the difference between having a torque that goes like sine of theta versus theta? Well, let's take a look at how theta and sine of theta compare to each other. Here is a plot of sine of theta. So this is sine of theta. And here's the origin right here, and sine of theta passes through the origin just like that. And then this is a plot of theta. So this would be like x equals theta, y equals theta. It's just a 45-degree angle passing right through the origin. What we notice is that obviously over here, sine of theta looks nothing like theta. Sine of theta is down here, theta is up here. Likewise over here, theta is down here, sine of theta up here. But what about near the origin, around in this region here? Well, we notice that they overlap each other quite a bit. In other words, when theta is small, and I'm talking about theta measured in radians. So not degrees, but when theta is measured in radians, when theta is small, then the value of sine theta is very, very close to theta. I mean, if we came in close enough, you couldn't even tell the difference between the two lines. They just look like they're overlapping. So when theta is small, sine of theta is the same as theta. That's called the small angle approximation for sine of theta. When theta is small, sine of theta is approximately equal to theta. Well, if we make that approximation, what can we do? So if theta is small, and what do we mean? How small does theta have to be? Well, it turns out that it's about less than or equal to 10 degrees. If you're less than 10 degrees, you're about 1% different between theta and sine of theta. So we'll say let's keep theta to less than a 10-degree angle. In other words, we limit the motion of our pendulum to 10 degrees back and forth, 10 degrees or less. In that case, sine of theta is approximately the same as theta. And you can do this on your calculator. You can check it on your calculator. Put your calculator in radians mode, put in some small value, and take the sine of that value. And the smaller the angle is, the closer the sine of the angle will be to the original angle. If you don't want to change it into radians, just take an angle and take the sine of that, but then the sine, convert that back from radians into degrees, and the original angle that you used would be very, very similar to that. Okay, so let's make this approximation. Let's assume sine of theta is approximately theta. What do we have? Then over here, sine of theta is going to be approximately equal to theta. And then we notice that the form of this is the same as the form of that, where rather than k over m is omega squared, g over L is omega squared. So everything that we have determined for the simple harmonic motion with the mass on a spring is going to apply to simple harmonic motion, or something that's close to simple harmonic motion, for the pendulum. So remember, what did we find for, let me erase this now. We are going to always assume now we're in the small angle approximation. We found that the period for the mass on a spring was equal to 2 pi root m over k. Well, we can just say now exactly what's the period. So this is for the mass on a spring. What's the period for the pendulum? Well, it's going to be 2 pi root, rather than m over k, we'll have L over g, L over g. This should then be the period of our pendulum. Well, let's give this a try. I don't usually do experiments in lecture, but let's actually try this. Let's set up a pendulum. I'll choose a pendulum with a length of 1/2 meter. We'll figure out what the period is, and then let's actually test it and see what we get. Okay, let's give this a try. I have got a pendulum here, and I have tried to set its length as close as I can to 50 centimeters. Hopefully that looks like 50 centimeters to you. Yep, looks pretty close, I think. Okay, something like that, 50 centimeters. Now, what do we get? If we put in 50 centimeters, 0.5 meters, the period is 2 pi root 0.500 meters divided by 9.8 meters per second squared. I get a value of 1.42 seconds. What we're going to do is we're going to measure this, but rather than one period, let's let it go for 10 swings, and that should give us a time of 10 times 1.42, or 14.2 seconds. Let's see how close we can get. Hopefully the timing will be the same when you actually watch this video, so you can actually time it yourself if you want. So I'm going to start this swinging, but remember, less than 10 degrees. Okay, now I've got a stopwatch here. I'm going to start this. Okay, so 1, 2, 3, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ooh, I got maybe you can't see this, I don't know, I got 14.02 seconds. 14.02, so we're off by 0.2 seconds. That's not too bad. That is definitely could be accounted by delay in pushing the button or something like that. Okay, very, very good. So that seems to work. Let's take a look at a different kind of pendulum, like I mentioned before, a physical pendulum, and see how that is different from a simple pendulum. This is actually called a simple pendulum. How does a physical pendulum differ from a simple pendulum?